Welcome back to the deep dive. Today we are opening a file that, honestly, it looks like a simple jewelry guide at first.
Right.
But you peel back just one layer, and suddenly you're in this really complex deep dive on, like, thermodynamics, crystal geometry, and market psychology, really.
Oh, absolutely. We're looking at a whole stack of industry briefs, some technical analyses, and they're all trying to explain this very specific, very confusing thing happening in the diamond market right now.
And the scenario is this. Imagine you're shopping for a lab-grown diamond. You're looking at two stones.
Okay.
They're both Marquise Cutso, that football shape.
Yeah.
And they're the exact same carat weight, exact same chemical composition. To the naked eye, they are twins.
On paper, at least, if you just glance at the top line of the certificate, yeah, identical.
Exactly. But one have a price tag that is significantly higher than the other. And I don't mean by a little bit. We're talking a real premium.
A noticeable one.
So the mission today is to figure out why. Because according to these documents, the answer isn't in the usual 4 C's. It's in the biography of the stone.
It really is. It all comes down to how it was born. We are wading right into the battle between two different technologies, HPHT and CVD.
Which just sounds like alphabet soup. But it's really the difference between, like, old school heavy industry and high tech. So let's get into this crystal code. Why does it matter so much how a diamond is grown, especially for a fancy shape like a Marquise?
To get the price difference, you have to get the machine difference. There are 2 ways to make a diamond. The first is HPHT.
High pressure, high temperature.
That's the one.
The brute force method.
Essentially, yeah. This is the original method. I want you to picture a massive 70-ton hydraulic press.
Wait, 7 tons.
These are gigantic building-sized machines. And the whole idea is just biomimicry. The Earth makes diamonds by crushing carbon under insane heat and pressure. HPHT is just us saying, okay, we can build a machine that does what the Earth's mantle does.
So we're literally just squeezing carbon atoms until they give up and rearrange themselves into a diamond.
Precisely. And it takes a monumental amount of electricity to maintain that pressure. It's hot, it's loud, it's very expensive to run. It is heavy industry.
Okay, so in the red corner, the giant hydraulic press. What's in the blue corner?
CVD, chemical vapor deposition. And this is a completely different animal. Instead of a press, think of a vacuum chamber, like a reactor.
Almost like a microwave.
A very, very high-tech microwave plasma reactor, yeah. You pump in some hydrocarbon gases, usually methane, and you use microwaves to spark a little plasma ball. That plasma breaks the gas apart, and carbon atoms literally rain down onto a little seed plate at the bottom.
So you're not crushing it, you're growing it. Layer by tiny layer, like 3D printing.
That is the best analogy for it. It's atomic 3D printing. And because you don't need a 70-ton machine, the whole operation is different. The reactors are smaller, they're scalable, you can fill a warehouse with them, you can grow a whole batch of diamonds in one go.
And that leads to the first big point in the data, which is market saturation. CVD is just easier to scale up.
Yeah. Exactly. If your goal is to make a lot of diamonds and bring the price down for everyone, CVD is your technology. It's just more flexible, more efficient to scale.
So broadly speaking, CVD prices dropped faster just because the supply is, well, almost infinite compared to the bottleneck of building another one of those giant HPHT presses?
Correct. But, and this is the key thing for anyone listening, that efficiency comes with a geometric cost. This is where we get into what the briefs call the square peg problem. This is where the price for our 2 Marquise diamonds really starts to split.
This was the part of the research that made it all click for me. I always assumed a lab diamond just grows as a sort of amorphous blob or something.
Nope. They have a native shape. Physics decides. When you grow a diamond in that HPHT press with pressure from all sides, it grows into a shape called a cuboctahedron.
A cuboctahedron. Okay, what does that look like?
It's a 14-sided crystal. It's blocky. It's chunky. It honestly looks like a rough diamond you'd imagine someone digging out of a mine. It has depth in all directions.
Right, it's a 3D chunk. So what does the CVD diamond look like when it grows?
Well, remember, it's raining down onto a flat plate. So it grows up. It forms a flat tabular shape. Think of a thick coaster. Or a hockey puck.
A flat disc.
A flat disc. Okay, so now you're a diamond cutter. You've got this flat disc. What's the easiest, most efficient shape to cut out of it?
Something. Flat and round.
Exactly. A round, brilliant. You can basically stamp round cuts out of a CVD wafer like you're making cookies. It's incredibly efficient, which is why for round diamonds, the price gap between HPHT and CVD is pretty minimal. The raw material matches the final product.
But we're not talking about rounds. We're talking about the Marquise.
The Marquise, the pear cut. The emerald cut, the fancy shapes, and the key thing about them is that they're long and they are deep.
Right. A good marquise needs that depth, that belly to really sparkle.
Mhm.
Otherwise, it just looks kind of dead in the middle.
Precisely. So if you take that flat CVD hockey puck and try to cut a deep, pointy marquise out of it, well, you run out of material. You hit the bottom of the crystal.
You just physically can't get the depth you need.
You're totally limited by how thick that crystal grew. So cutters face this awful choice. Either they cut a shallow stone, which just looks lifeless and glassy.
Or they have to grow this ridiculously thick, expensive piece of CVD just to cut one skinny little marquise out of it, and they grind away most of the diamond they just grew.
Yes. The yield is terrible. It's, like you said, you're forcing a flat disc into a deep hole. It doesn't want to go.
But with that HPHT chunk, the kiboctahedron,
It's already 3D. It's already got the depth. A cutter can look at that rough crystal and orient a perfect marquise inside it. They get better proportions, and they save way more of the carat weight.
so a big chunk of that price premium is just basic economics. The HPHT rough was sort of born to be a marquise. The CVD one had to be forced.
That's the geometric argument, yes. And it's a huge deal, but for you, the person buying it, the rabbit hole goes even deeper. We have to talk about the purity paradox.
This is the part that really got me. You see all these ads saying lab diamonds are chemically identical to mined ones? I just assumed that meant they were all, perfect.
It's a bit more complicated. It's a tint issue, really. It's just inherent to the CVD process. When you're growing them fast, if there's even the tiniest leak of nitrogen into that chamber, the crystal lattice can get a little distorted. And that often creates a slight brownish tint.
Brown. Not a color I'm looking for in a diamond.
No one is. In the industry, they call it muddy. Now, on the other hand, HPHT, because it's so close to how the Earth does it, it's exceptionally good at producing what are called as-grown colorless stones. We're talking D, E, and F color grades right out of the machine.
As grown, I saw that term over and over in the briefs.
It's a really critical distinction. As grown means the diamond you hold in your hand is exactly how it came out of the growth chamber. Nothing's been done to it.
Wait, which implies that the brown CVD stones are being doctored.
And this is the irony of it all.
Yes.
To get rid of that brown tint in a CVD diamond, producers often put it through post-growth treatment.
And what is that treatment?
They put it in an HPH2 press.
You cannot be serious. So the futuristic 3D printed diamond has to go into its competitor's brute force machine to get fixed.
That is exactly what happens. It's a process called annealing. They use that high pressure and heat to basically realign the crystal structure and bleach out the brown color.
So if I buy a perfectly white CVD diamond, there's a good chance it was actually grown brown and then cooked a second time to turn it white.
It's very, very common. And look, the final diamond is white. Maybe you don't care. But in the trade, there's a premium for purity. It's like an unheated sapphire versus a heated one. The as-grown HPHT diamond gets a higher price because it was born perfect. It didn't need a facelift.
It's the difference between natural beauty and, cosmetic surgery.
Yeah.
Even if the result is similar, the market value is the one that didn't need the help.
Especially for marquise. Because fancy shapes, they hide nothing. A round brilliant has 57 facets. It's a hall of mirrors designed to bounce light everywhere and hide flaws. But a marquise or an emerald cut, they're like big open windows. If the material itself is hazy, you're going to see it.
Which brings us to visual crispness. The notes mention something about striations in CVD. That sounds like a flaw in the actual fabric of the stone.
It goes right back to that 3D printing analogy. CVD grows layer upon layer upon layer. If that process is rushed to save money, which it often is, the diamond can develop these internal grain lines, striations.
Like the rings inside a tree.
Exactly like that. Now, this might not even show up on a grading report. The diamond could be a VS1 because there are no big black carbon spots. But those grain lines, they mess with the light. They create a haziness, a milky quality.
So the diamond just looks soft or sleepy.
Sleepy is a great word for it. Oily, some people say. It just lacks that electric fire. It's the difference between looking through a freshly cleaned window and one that's got a month of grime on it.
And HPHT doesn't have these layers.
No. Because it grows under constant crushing pressure from all sides at once, the crystal is more uniform. The light just passes through it cleanly. The sources describe high-quality HPHT as looking ice-cold or super transparent.
Okay, so let's connect this to the bow tie. I know ovals and marquise cuts always have that little dark shadow across the middle. That's just part of the cut, right?
It is. It's light leakage. You can't totally get rid of it, but the quality of that shadow makes all the difference.
How can a shadow have quality? It's just dark.
Ah, but in a diamond, it's different. In a CVD stone that has that internal milkiness we were talking about, the bow tie can look mushy. It looks blurry, like a smudge on your glasses.
Gross.
But in a super crisp HPH2 stone, the bow tie tends to be sharp. It's distinct. The edges are clean. It looks less like a flaw and more like a deliberate, cool contrast pattern.
So in one, it looks like a design feature, and in the other, it looks like a defect.
Exactly.
Yeah.
And for our keys, which is all about drama and sharp points, you want that crisp, high-definition look. You don't want soft and mushy.
Now, I do want to push back on this a little because the data also says HPHT isn't always perfect. It can have its own tint, this blue nuance.
Yes, that's the other side of the coin, absolutely.
So if brown's bad in CVD, why is blue okay in HPHT? Isn't it tint to tint?
Technically, yeah. On a lab report, a blue tint can lower the color grade just like a brown one, but our eyes and our brains perceive them in totally different ways.
What causes the blue?
It's boron, the element boron, the same thing that makes the Hope diamond blue. Sometimes trace amounts of it from the growth cell get absorbed into the diamond.
And people like this.
They often prefer it. Think about it. Laundry detergents use bluing agents to make whites look whiter. A tiny hint of blue counteracts any faint yellow and makes the diamond look whiter than white. It gives it this cool, steely, metallic look.
So the brown CVD tint feels like an old sepia photograph. It feels aged or dirty.
Yeah.
But the blue HPHT tint feels like a cool, modern Instagram filter.
That is a brilliant analogy. Even if the certificate says it's a slightly lower color grade, your eye sees the blue nuanced stone as brighter and crisper.
It does sound a little like marketing spin, though. It's not a bug, it's a feature.
To an extent, it is. But in the world of luxury, perception is reality. A customer might see that blue nuance and think it looks like a super rare natural diamond. Nobody ever mistakes a brownish CVD for a rare collectible.
Okay, so let's zoom out to the whole market. We have these two technologies. One is scalable and flat, but can be a bit brown and hazy. The other is heavy, geometric, and super crisp. How is the industry actually positioning these?
They're creating a tier system. It's the classic Toyota versus Ferrari dynamic.
With CVD as the Toyota.
Right. It's reliable, it's accessible, it's great for most people's everyday needs. If you want a beautiful round brilliant for a pair of earrings or a classic engagement ring, CVD is a fantastic choice. The price is great, and the round cut is very forgiving of that internal graining.
And HPHT is becoming the boutique high-performance option.
Specifically for these fancy shapes, yes. The sellers are framing it as the connoisseur's choice. The sales pitch is, look, this stone was born to be a marquise. It has the right internal structure. It's as grown. It's pure.
It's a story about integrity.
And that story justifies the price premium. You're not just paying for carbon atoms, you're paying for the better raw material that leads to better optical performance in that specific cut.
It's just so fascinating. We started this wondering why two identical stones were priced differently. And after digging into it, it turns out they're not identical at all.
Chemically, yes,
Yeah.
but physically, structurally, they are very distinct materials.
So let's give a final practical takeaway for anyone listening who might actually be shopping. If I'm buying a standard round diamond, should I care about any of this?
Honestly, probably not that much. The round cut is the great equalizer. You can probably save some money with a well-cut CVD and get a stone that is absolutely stunning. The faceting just hides a lot of those subtle issues.
But if I have my heart set on a marquise, or an oval, or an emerald cut,
And you need to be asking the question. You should ask to see the growth method on the report. Look for the term as grown. Look for that visual crispness. An HPHT stone just starts with a better piece of rough for that cut, and you're much more likely to avoid that mushy bow tie.
so for fancy shapes, the premium is probably worth it.
In my opinion, yes. If you're buying a shape that's supposed to be sharp and dramatic, you want the material that can actually deliver that look.
You know, this whole thing makes me think about our idea of perfection. We invented lab diamonds to kind of hack the system, to get the beautiful gem without the mine.
Right, to manufacture perfection.
But even in the lab, we end up valuing the process that mimics nature's struggle. We pay more for the method that uses 70 tons of crushing pressure than we do for the one that just uses clever chemistry in a vacuum.
It is really ironic, isn't it? HPHT is the closest we can get to the violent geological reality of how a diamond is actually made on Earth.
And CVD, the cleaner, more elegant, high-tech method,
Yeah.
is seen as the shortcut. It's like even when we make something ourselves, we still respect the pressure. We want to know our diamond went through something to become beautiful.
Maybe we just value things that are hard to make. Or maybe, the Earth had it right the first time, and the closer we get to that original recipe of just immense pressure and heat, the better the final result is.
Or maybe we just really like things that sparkle in high def.
Yeah.
Either way, next time you see marquees, you'll know the secret question to ask. Was this crushed or was it printed?
A very valid question.
Thanks for diving into the crystal lattice with us today. We'll catch you on the next one.
Take care.